Rational numbers can be written in the form p divided by q, where p and q are integers. Numbers that cannot be written in this form are irrational numbers. Irrational numbers that involve roots are called surds. There are two rules that we use when we simplify surds. Firstly, when we multiply a root by a root, we can write this as the root of those two numbers multiplied together. And secondly, when we divide a root by another root, we can write that as the root of the first number divided by the second number. So to simplify root 3 times by root 3, we use the first rule to multiply two roots together. This tells us that we can write root 3 times root 3 as root of 3 times 3, which is equal to the square root of 9, and we know that the square root of 9 is equal to 3. Now don't forget to fill this in your booklet. This question is much harder as there are 4 terms. As there are multiply and divide, we should use BIDMAS, which tells us we must do the divide first, which means we can rewrite this as, we can then do the rest of the question in order. So if we just concentrate on the first 2 terms, we can use the rule for multiplying surds together to get square root of 6 over 6 times by square root of 11 over 3. Square root of 6 over 6 just simplifies to the square root of 1, which is just 1. So we end up with 1 times the square root of 11 over 3. So our final answer is simply the square root of 11 over 3. To simplify this question, first we need to expand the brackets. So we get 3 root 6 plus root 6 times root 3. We can then use our law for multiplication of surds. So that gives us 3 root 6 plus the square root of 6 times by 3, which we can simplify to 3 root 6 plus root 18. We can try and see if we can simplify this further and see if root 18 will simplify. So root 18 we could write as the square root of 9 times 2, because that would allow us to write that as the square root of 9 times the square root of 2, and we know that the square root of 9 is 3, so we end up with 3 root 2, which gives us a final answer of 3 root 6 plus 3 root 2. We can only add and subtract surds if the number inside the root is the same. In this case it's not, so we need to see if we can simplify both surds so that we end up with 2 terms with the same number in each of the roots. To do this, we need to find a number that will multiply by a square number to give us the number inside the root. So if we start with 240, 16 is a square number that goes into it, and we times 16 by 15 to get 240. We can also see that 15 goes into 60, and we would multiply it by 4, which is also a square number, allowing us to simplify both of the surds. So the square root of 240 we can write as 15 times 16, and the square root of 60 we can write as 15 times 4, We can then use our multiplication rule to split up these surds, and we can write it as square root of 16 multiplied by the square root of 15, take away the square root of 4 multiplied by the square root of 15. The square root of 16 is 4, which gives us 4 root 15, and the square root of 4 is 2, so we get 2 root 15. And now, as the number in these square roots are the same, we can do the take away, and we end up with 2 root 15. This question is very similar to the last one, except this time we're doing an addition. We need to find a square number that goes into 40. So 4 is the obvious one, which would give us 4 times 10. 10 goes into 90, which would also give us 9, which is a square number, so we could simplify both surds this way. So writing this down, the square root of 40 we can write as the square root of 4 times 10. And the square root of 90 we can write as the square root of 9 times 10, which is the same as the square root of 4 times the square root of 10 plus the square root of 9 times the square root of 10, which simplifies to 2 root 10 plus root 10. And now, because they've both got root 10, we can add them together, and that gives us 5 root 10. This question looks harder as there's a fraction, but we need to do exactly the same as before. We need to make sure we have the same number in the square root. If we take the first fraction, we can write it as the square root of all of 9 multiplied by 5 over 7 plus the square root of all of 25 times 5 over 7. We can then simplify the first fraction to give us the square root of 9 times the square root of 5 divided by the square root of 7 plus the square root of 25 times the square root of 5 divided by the square root of 7. Square root of 9 simplifies to 3, which gives us 3 root 5 over root 7 plus the square root of 25 simplifies to 5 root 5 over root 7. We've now got the same numbers in the square roots, so we can add them together. 3 plus 5 gives us 8 root 5 divided by root 7. And to make it look a little bit neater, we can combine the square root again and get 8 times the square root of 5 over 7. We're now going to look at indices. So given a term such as x to the power of 5, x is called the base, and the number 5 is the index power or exponent. Rational numbers are numbers that can be written as a divided by b, where a and b are integers, and we can also use index laws that we'll look at in a minute with any rational numbers too. We have lots of rules when working with indices, as you can see here, and we call these our index laws. Firstly, if we have a number with a power times by a number with a power, we can write that as that number to the power of the two powers added together. Similarly, when we divide, we do the same, but we write the power as the first power minus the second power. If we have a number with a power inside a bracket to another power, we can multiply the powers together. But if we have two numbers in a bracket to a power, that's the same as each number in the bracket to that power. x to the power of 1 over n is the same as the nth root. And this is a more complex version of that, where x already has a power. We end up with a fraction of a over b. X to the power of minus n is the same as 1 over, so the minus power indicates we get 1 over x to that power. X to the power of 0 is 1. Anything to the power of 0 is always 1. If we have a fraction, so a rational number, to a minus power, that is the same as flipping that fraction just then to the power of a, not minus a. We can simplify fractions that contain indices. As long as there is only one term on the bottom, we can divide each term on the numerator by that one term on the bottom of the fraction, and then simplify each term using our indices rules. If we have a look at an example, we can only multiply indices together when the bases are the same. So firstly, let's start with the numbers. So 2 multiplied by 3 gives us 6. M to the power of 4 multiplied by m to the power of 3 gives us m to the power of 4 plus 3. And n squared multiplied by n to the power of 9 gives us n to the power of 2 plus 9. We can then simplify this to get 6 m to the power of 7 n to the power of 11. Make sure you fill this in your booklets. This example is more complicated, so let's make sure we use big maths rules and firstly look at the bracket. When we divide, we take away powers, so let's do the 4 divided by 2 first, which gives us 2. D to the power of 5 over 3 divided by d to the power of 1 over 3, we can write as a subtract in the power. And then let's simplify each of the following terms. So if we look at the next term, the whole bracket is squared, so that means we square each term inside. So that gives us 3 squared d squared divided by 3. And the last term is a rational number to a minus power, which is the same as flipping the fraction and writing it to the power without the minus. We can simplify further now, so if we take the first term, we get 2d to the power of 4 over 3 times 9d squared over 3, which simplifies to 3d squared, times by d to the power of 3 over 2 divided by 4 to the power of 3 over 2. We can combine the first two terms, so 2 times 3 gives us 6. D to the power of 4 over 3 times by d to the power of 2 gives us d to the 4 over 3 plus 2. And we can then simplify our fraction to d to the power of 3 over 2. And 4 to the power of 3 over 2 is 8. Again, we can now collect the terms together, so we end up with 6 divided by 8, d to the power of 4 over 3 plus 2 plus 3 over 2. We can simplify the fraction to get 3 over 4, and if we add all the powers together, we get 29 over 6. In this question, we have one term on the bottom of our fraction, so we can divide each of the terms on the top by this, which gives us 3x to the power of 5 divided by x to the power of 4. plus x cubed divided by x4. We can now use our index laws. So 3x to the power of 5 divided by x to the power of 4 tells us we can minus our powers, giving us 3x to the power of 5 minus 4 plus x to the power of 3 minus 4. And we can simplify this to get 3x to the power of 1 plus x to the power of minus 1, which we can also write as 3x plus 1 over x. Again, this question looks harder, but we do it in the exact same way we did the last question, and we divide each term on the top by the term on the bottom. This gives us 3x squared over 2x to the power of 7 over 3 plus x to the power of 8 over 3 divided by 2x to the power of 7 over 3. If we look at the first term, we can simplify that to 3 over 2 and then use our rule for dividing by powers, which gives us a power of 2 take away 7 over 3. And again, we can simplify the second fraction, again using our divide law. We can then simplify our powers and get 3 over 2 x to the power of minus a third plus a half x to the power of 1/3, which if we use our index rules we can also write as 3 over 2 the cube root of x plus a half cube root of x. We can use the rules we've learnt to solve more complicated problems. So if we have a look at this question, the first piece of important information is that a flower bed has sides of length x and 8x. We're also told that there are 6 flower beds around it, each with an area equal to the cube root of the large flower bed. And we're asked to find the total area. So the first thing that we can do is we can write down the area of the large flower bed, which is equal to x times 8x, which gives us 8x squared. We can then work out the area of one small flower bed, which is equal to the cube root of the large flower bed. But we have 6 of these, so the area of 6 small flower beds are equal to 6 times the cube root of 8x squared. So this is what we want. We want the total area covered by the 6 small flower beds, but it wants the answer in index form, so we need to simplify this answer using our index rules. The cube root is the same as writing 8x squared all to the power of 1 over 3. And when we have a bracket with a power on the outside, we need to do each of the things to that power. So that gives us 8 to the power of a third times x to the power of 2 over 3, using the rule that we multiply the two powers together. 8 to the power of a third is the cube root of 8, which is 2. So we end up with 6 times 2 times x to the power of 2/3, and then we can simplify that to give us 12x to the power of 2 over 3. So again, we need to read this question carefully. We want a formula relating to brain mass and body mass. If we read the question, we're told that the brain mass is approximately 1/100th of the cube root of the square of its total body mass. So for part A, we want a formula relating brain mass, B, to the total body mass. So B is equal to 100. So 1 divided by 100 of the cube root of the square of its total body mass. And its body mass is represented by m, so that gives us m squared. Which, if we use our index rules, we can write as m to the power of 2/3 all divided by 100. This makes doing calculations easier. So when we get to part B, part I wants the brain mass of an animal with a mass of 3.375. So m is equal to 3.375, which we can substitute in to get b is equal to 3.375 to the power of 2/3 divided by 100, which we can use our calculator to calculate, giving us 0.0225 kilograms, or 22.5 grams. II is slightly harder, as this time we're given the brain mass. So the brain mass, B, is equal to 202.5 grams, which we need to change into kilograms. So it gives us 0.2025 kilograms. So if we use our formula, 0.2025 is equal to m to the power of 2/3 divided by 100. We can make this simpler by multiplying by 100. So 20.25 is equal to m power of 2/3. And if we cube and then square root both sides, we get 20.25 to the power of 3/2 is equal to m. Again, using our calculators, this gives us m is equal to 91.125 kilograms.